Alright, at this point, hopefully you did not pull out your hair while attempting the new advanced rendering challenge that we've given you for part 2 of Knowledge Review number 7. Now in this video, Logan is going to show you how you could go about coding it in. Now as I said, we're not going to trace this out on a whiteboard for the simple fact that we would like for you to try it if you had any problem coming up with the logic yourself. Think of it as kind of reverse engineering. Have no fear though, of course we're going to explain what every single line of code does, but it's pretty sophisticated. There is some recursion going on. There's a little bit of understanding of how strings are being built. And we're also going to use the string builder, which is something we've never done before. So there's a little bit of new stuff in here. But once again, once we get all the way through the method, take the time after the video to try to trace it out yourself with a very simple hierarchy and see how it actually flows on paper. So with that, Logan, let's go ahead and get started.
All right, well, the first thing that we need to know is exactly how are these lines being drawn from within the tree utility.
Okay.
Now, while they look like connected lines, there's actually nothing that special about them. If I select over any of these, we can see that these characters are all individual characters, so we don't have to worry about any actual graphical line drawing. What we need to worry about is how can we assemble a series of characters such that they connect. The other question to answer is what characters are these that are being used such that they connect? They're obviously not the hyphens because we saw from our own renderer that those were dashed and had spaces in between.
Okay.
To answer that question, we need to load up the Windows character map, which I have already loaded here. Generally, this character map is found within the accessories section of the start menu. Now, inside of the character map, if we scroll down near the bottom, we're presented with a set of lines and angle brackets and T characters. These are the actual characters used by Tree to draw these connecting lines. More specifically, the ones we're interested in are horizontal lines, vertical lines, the right angle bracket, and the right T bracket. These lines are what makes up all of the lines seen here by the renderer. The next question is how do we draw these from inside of C#? Because I wouldn't want to rely on simply copying these to the clipboard and then into the actual text buffer. It would be cleaner to be able to use this character code to generate an actual char inside of C#. So let's begin by taking a look at that. What I want to do is set up a set of constants, first off, so that I don't have to remember this number every time I go to draw it. And then we'll see how to fill that constant with this actual data. So now back over to C#, I want to load up the transform node so that I can set up all of our constants inside of the transform node. I'll begin with the horizontal line. And what I'll use to define that is a private constant char, and we'll call this char underscore hline as the actual name. Now, I want to be able to set char hline to the value from the character map, which you can see here. Well, that's not the horizontal line, but these numbers are in hex, as we can see by the T bracket being 251C. So I need to enter this as hex over in C#. This is done by doing 0 by and then the number given here. Now the first one we're interested in is the actual horizontal line, which is this character, and has a character code of 2500. So back over to C#, we'll define this first a cast to char, since I'm going to be defining this as a literal. And the value we're going to enter is 0 by 2500.
So that it knows to treat 2500 as hex.
Right. Alright, that takes care of the horizontal line. Next is the vertical line, which I will name char underscore v line.
Okay.
Then we'll jump back to the character map to get the code, which is 2502. So we'll change this to 2502, and that should represent our vertical line. After that, we have the T-joint character. So I'll name this char underscore T-joint.
Wait. I think you just lost your vertical line.
Oh, whoops, I overread it. Wrong. Oh, yeah, I just did the wrong. There we go. Char T-joint. And the T-joint character that we were looking at had the character code 251C. And 251C. And the last character that we need is that right pointing angle. So I'll define this as char angle. And the angle character code from the character map is 2514. 2514.
All right, now that you have all of these characters stored in character constants, what's next?
Well, next, I want to take note of the spacing that's used here. Just visually looking at this, we can see that each subsequent node is spaced more than we have in our current version. So the first thing I want to do is figure out what that spacing is, and then store that in a constant as well, so that it's in an easy-to-change location.
Sounds good.
Now, in order to get the spacing, since I have the prompt in select mode, I can simply select over the number of characters Y that this is. So here's our first character, second, third, fourth. And if we go over, we hit the line. So that's 4 characters of spacing between everything.
Okay.
So I'll define a simple constant for that character, or for that length of 4. So I'll make a private constant, this time an integer value, called treeDrawOffset. So treeDrawOffset, and set that to a value of 4.
The nice thing is we can come in here later and change it to 2 or change it to 8, whatever we need to get the look we're looking for.
Right, or if we ever made list configurable, so we could give an input as a parameter.
There you go.
Alright, that has all of our constants and our drawing offset set up. The next thing I want to do is I want to put an example tree in place. Since I want to give at least a somewhat complex tree that has a few levels deep, so we make sure we test all aspects of the render.
Right.
Now, to do that, I want to hard code in a tree back in the program.
Yeah, the bottom line is you don't want to have to launch this application every time you check any tweaks you've made to your rendering code. You don't want to have to go in there and say sphere, light, parent it, make another object, parent it, make another, and keep doing that every single time. So this will just kind of be pre-generated.
Right. Now, before I turn focus away from the transform node class, let me rebuild, make sure I haven't induced any errors. Everything is building fine, so I'm going to shift my focus momentarily over to the program class, where I'll set up our example tree. Now, we actually had a few things, a light and a shape node being created. I'm going to erase those out and replace them with a new example scene. This is going to be constructed entirely from transform nodes. Since I'm not worried about naming in this case, I'm just worried about the hierarchy. So we'll begin. Now, what I want to do for this example node is just have a set of transform nodes named A through H and have them parented in a certain manner. So I'll begin with transform node A, and we'll need to turn around and create a transform node and give it the name A. Then I'm going to copy this and paste it 7 more times. So A, 6, 7, so that I can give these names A through H. So we have our nodes A, B, C, D, E, F, G, and one more. Yep. And then H. And we need to turn around and do the same thing for the names. So B, C, D, E, F, G, and finally H. And if we were to turn around now, we want to have, while we're at it, we might as well put in a manual call to the list command. So I could call up the command manager. If I could spell command manager, and we could tell the command manager to process the command instead of having to type it every time. And the command I would like to process is the ls command.
So if we run this real quick, we'll just have a bunch of nodes at the root level. And we do. Very nice. So let's go ahead and assemble some sort of hierarchy now.
Alright, and we can do that by simply calling setParent on any of the desired nodes. I'm going to begin with node B, and I'm going to parent it to node A. And I'll copy this line to make it quicker since there's several things we need to parent. The next thing I'd like to parent is to parent the node C to node B. Then I'd like to parent node E to node D. Then parent node F to node D. Then parent node G to node D as well. And then finally parent node H to node F.
Alright, let's run that again, make sure everything is now assembled into a hierarchy. And it is. So we can see A has a child B, which has a child C, and then D's back at the root with child E and F, which F has a child H, but D also has another child G. So very good.
Alright, and that will give us our example hierarchy so we can test the more advanced renderer. Alright, and that really just leaves the renderer itself now.
Okay, so what we can do is just slowly start building the renderer up so that they can get a really clear picture of what's taking place.
Right, just build it in a more simple state and then move on to more of the advanced line drawing as we get deeper into it. So what I want to do now is switch back over to transform node and then jump down to our renderer as it is implemented here in showTree. I'm going to take the entire showTree method and comment it, just so we can refer back to it if there's any piece of the code that we need from within it. Though the idea here is that we completely rewrite the entire method. Now the way I'm going to rewrite this is it's going to take in the depth, as we see here, but it's also going to take in a list, because I'm going to change the overall behavior of ShowTree to make it cater better to doing the advanced rendering all in one go.
And not only that, you're also going to change it from being a method that's behavior on an instantiated instance of node. Instead, you're going to make it a static class as well.
Right. I'm going to change the way this works where the existing ShowTree operated for its current node. So we access things that were part of the state of this node. The way I'm going to change it is just that the method itself is static and a list is handed to it manually.
That's right.
So this is going to be a private, spelling, private static method, still going to be void. And we're going to still call it ShowTree. But now we're going to take in a list of nodes to operate on. So instead of just using this node's current list, we're going to allow a list to be specified. So a list of transform nodes will be given to ShowTree, and this list will be called node list. And we're also going to specify the integer depth, just as we were doing in the last one. Alright. Now, what do we want to do next? Well, I'm going to begin with all of what I'm going to term simple operations, the things that can be done regardless of where this node is in the hierarchy. The first of which is to define our initial spaced padding.
Okay.
And also get into the string builder you had mentioned. Mm-hmm. Since there's going to be a lot of string operations done in this version of ShowTree, I'm going to use the string builder since it's much faster at appending as opposed to string concatenation.
Both much faster and much more efficient, which we'll talk about that in later lessons. But we're going to go ahead and use it here.
Okay. So I'm going to begin by defining a string builder. And I'm going to call this string builder SB, and then create a new string builder. Now, the next thing that we're going to do, the way this is going to work basically is we're going to take the string builder, append any series of strings to it, and then turn around and show its output using a console write line. The first thing that I want to put into the string builder is our padding off of the left, so a number of spaces based on our depth. I'll do that by using our string builder's append method. Append works and can take in several different types of information, strings, chars, and so on. But one thing that's interesting about it is one of its overloads allows you to take in a single character and then repeat that character a number of times.
That works out very good here.
This works out very handy for padding, so we don't have to rely on something like pad left of a string. The character I'm going to use is the character space, and the number of times I want to pad is our tree draw offset times our current depth within the hierarchy. So times the given depth parameter. So that should give us a number of spaces. So 4 spaces per level of depth.
Makes sense.
The next thing that we know that we're always going to have, as a matter of fact, I can bring up the tree app to show this, and that is every name is preceded by a number of horizontal lines, whether it's connected by a T-joint, an angle bracket, or whatever. No matter where it's at, we're always going to have these number of lines. The exact number of horizontal line characters, if we count them out one by one, is 3. So we can still use our spacing, because we have our 4 spacing if you include the angle or T bracket. But we know that no matter what that character is, we're always going to have 3 of them. Or, in our terms, tree draw offset minus 1 characters. So we could turn around, and the next thing we can append is that character. We've stored that character in a constant. We've got a constant horizontal line to store it. And I wanted to use the same operation for repeating it a number of times. So we use an overload that takes in a char, and then tree draw offset minus 1 so that we get 3 actual horizontal line characters.
So now you have a series of spaces immediately followed by a line made up of 3 different of those horizontal lines.
Exactly.
Okay.
Now, one other thing that we know that we're always going to have when printing out the name of a node is the name of that node.
Right.
So I can turn around and put that in as well. Though instead of using append by itself, I'm going to use append format. This will make it easier to include the name of the node and the name of the shape node without having to do a bunch of concatenations.
Which is what we're trying to avoid here, taking this string plus this string plus this string.
Right. So append format is going to take in a string to specify the formatting and then a series of possible arguments. The first argument I want to give is the name of the current node, which actually one thing that I've left out as far as the loop I'm going to use to show this.
That's okay.
But we need the the name of the current node within the node list.
So let's just say that we're in the middle of a loop, and let's say we're going to use I as our index that's going to run through. So you have I available. Let's just stipulate that at the moment.
So node list I, so basically any one of the elements within this node list would be a node.
Right.
And that's what we want access to. So if we were within a loop, we could say node list and then some index. If I specify I as the value, that would be one of the elements if I was using I for an index in a loop. So I could say that node, and I don't need to specify anything afterwards because we've already have toString overridden so that we get the correct name.
That's right.
Now the other thing that needs to be included in this name is the name of that node's shape. So I could copy that, specifying that this is a node, then we should be able to do something like this. Node list I dot shape. Now for the actual formatting, what I can do is specify a string format and then include these as arguments. An argument is specified with curly braces and then an index. So if I did an open closing curly brace with a 0, that means it's going to be looking at this argument, node list I. Whereas if I did an open curly brace and a 1, we're now looking at this argument. So what this would show is one node, comma, another node. The actual format we want to specify is similar to the old one where we had a space and an open square bracket. So there's our space, and we can put argument 1 in square brackets, and then we should have the proper formatting. Now, of course, we've just been stipulating that this is within a loop, as I had left out one of the key parameters, or key things to this entire
What are you saying? You didn't leave it out. It was planned. And now they can see the importance of it because we need to deal with the nodes individually within this list. See? Huh? It's all planned.
Oh, that works.
So let's go ahead and put the loop in now.
The idea behind this version of ShowTree is that we need to take in a list and loop through it. So to loop through it, we could use a simple for loop, where we'll loop through loop until we reach the end of the node list's count. And then I can simply move all of these things, and suddenly node list I makes sense. I being the current index we're looking at inside of this list. So if we pull an element out, we would do so by saying node list I.
Okay.
And at this point, the method itself is actually only two things away from working. We've got a string builder assembled through a series of appends. Now we need to turn around and write out whatever is stored inside of that string builder. We can do that with our console. We can write out a line, and the result of that write line will be the string builder dot toString. And then one more thing we need to do is this method still needs to work in a recursive manner. That means after we're done with a given element, we need to turn around and call this method for this element's children list, so that the hierarchy will continue through children and so on. So that means we need to call ShowTree again, this time feeding it node list I dot children. So we step one level down into the next list of children. We also need to specify that the depth has gone one level deeper, so we'll give depth plus 1 as the depth parameter. And with that, the method should now work at this point, though if I build, you'll see that there's a few errors. What those errors are showing is the fact that there are existing calls to ShowTree that aren't taking into account the fact that we need to pass a list. The first of these that I'll address is the the private ShowTree, and this can simply be done by saying, since we're looking at ShowTree for a specific node, what are we actually looking at? We're looking at that node, or this dot children. That will be a valid node list that we can hand on to ShowTree.
You see, one of the really cool things here is now we have a static ShowTree and we have an instanced ShowTree, which actually belongs to each object that exists.
Right. ShowTree, in this case, now has two purposes, where originally it was simply to pass along 0 to give a proper starting point for depth. Now it's serving two purposes. It specifies where in the list, or which list we should start at, which is this node's children.
The children for our children, send it off to show the tree.
Exactly. Now if we build that, which should correct this line, now we have one line left, and that is in the workings of show all. Show all is interesting in that it actually becomes more simplistic using this renderer. I'm actually going to comment both of these. Really, I could probably just delete them. And the idea here is that show all should show everything from the root. And in the past, we didn't have any one root node. Instead, we had to go through all of the root nodes with a loop. Now, since this renderer has been changed from, you could say, node-oriented over to list-oriented, we do have a single root list that can be passed, the root nodes list.
That's right.
That means we could do a call to ShowTree feed it root nodes as the list it is to operate on, and then again specify depth to 0, and that alone should have it patched up and working. So at this point, we should be able to run and see what our new renderer is doing. So if we run, well, obviously not complete, as we weren't expecting it to. It's not done yet. But we are seeing proper depth spacing based on where the nodes reside in the hierarchy, and we're seeing the horizontal line. So while it's nowhere near done, it is certainly approaching somewhere.
Right.
All right. The next thing that we can address with this renderer is how to handle the T-joints versus the angle joints. Because we need to decide what's going to define when we show a tree joint versus an angle joint.
And looking at it logically, it's pretty simple if you think about it. If you have, well, let me just grab a mouse real quick and let me just show them. So here we are about to render a node. If this node has a sibling, then obviously we're not at the end of all of the nodes in that list. So we'd want to use a T-joint. So look at this node here. Does he have another sibling after him? No. So would we want to use a T-joint? No. If we did, it would just leave kind of a little stick sticking out there. We'd want to use an angle to end it all off.
So really it's very simple to decide on if you need a T or an angle, because the angle means end of list at this depth.
Exactly.
So that is a check which we can do with a simple if statement. What I'm going to do here is jump up just before we drew the horizontal line and put in such a check. We can do an if to see where our current index is in the list. We know that if I is less than node list dot count, we know that this is going to represent the very end of the list. If we said -1, this is going to be one in from the end of the list. Or whoops,
you almost hit the 1.
I see.
He didn't realize, guys. I just leaned over there and hit the 1 for him.
I was looking away from the screen to explain and hadn't realized that all the code was there. But what this means is, as long as I is 1 less or is less than the very last node.
Right.
So that means if this condition is true, we need a T-joint. Otherwise, we need the angle joint to represent the end. So if this was the case, then we need to append to the string builder an angle joint. So we can say sb.append, where we'll append the char T-joint. And otherwise, we need to append the char underscore, well, there we go with typing. So char angle will represent the end. So we've got our set of spaces, a joint or an angle. So at this point I should be able to build and run.
Ooh, a little closer.
And look at that. The A through C tree is now looking pretty much correct. Everything connects up. The tree off of the D node has 2 proper T-joints, an angle, but is now missing something. And if we look all the way over to the left, we're also missing a character here. So at this point...
And just think about it for a second. Just stare at this tree and think about why it's missing that character. Because where was our focus at when we were drawing? We were all the way into here. We never handled this. This is just all of our spacing that was because of the depth and the multiplication that was taking place with our padding and all.
Right, depth is always being calculated as a series of spaces. We're never putting any consideration in for vertical lines.
That's right. So now we've got to come up with some sort of system that's going to allow us to put correct vertical lines in to represent that we've got another child for that parent that's going to be coming up later, while, of course, at the moment we're drawing this part of the hierarchy.
And that's a tricky thing to consider, because let's say we're in the position of drawing this H node. Over here, we don't know about E or F, because we're all the way down into the hierarchy in H.
That's right.
That means we'd have to do some form of reverse lookup if we were to get back to this level. And then something else to consider is we might have a more complicated network, like in this tree example, where it would be inefficient to go all the way back up to some higher level to try to figure out what to draw. So what would be more efficient in this case is to, as we're drawing, let's go back to the example of E and F here. As we are drawing these nodes, if we know, like let's say we're looking at F, if we know a G node is going to happen, why don't we draw a vertical line, but instead of actually drawing it immediately, pass it on to the next level deep and let it use that and draw it. So basically assemble the padding ahead of time before we get into a level.
So we're not just going to take on the account for the padding being just a whole bunch of spaces and then our 3 lines.
Right. Instead, we'll actually calculate a string padding and then pass that instead of simply passing a numerical depth.
Sounds good.
So what we can do is we can change this parameter, instead of being an integer, to being a string, and I should probably close the example up before I do
maybe.
that. Alright, we could change this to a string, and we could call that string padding. So we specify the actual padding to be used by this iteration of the show tree. Now with that padding, what we'll do is, instead of appending spaces blindly, we'll instead append the padding itself. So this is where we go back to the fact that padding actually has to be handed to us by a previous iteration of show tree. Now the next thing that I want to do is create a string builder to handle adding on another layer of padding to the already given value. So that means I'm going to define a new string builder. I'll call this one pad builder. And we'll create a new string builder. And then we'll immediately turn around and append the existing padding to that pad builder string builder object. So what we can do with this now is we'll first take any existing padding that might exist and put it in the string builder to be shown. Then we'll take that same padding and put it in our pad builder to be added onto. And the reason for doing this is the one place throughout this method where we know whether or not we need a vertical line is inside of this check. This is where we can tell if we have any more sibling nodes or if we're at the end. Because if we have more, then the next level deep is going to need a vertical line. If not, there needs to be no line. So let me put some curly braces around this if statement, since I have more things to be put inside of the cases. And let's focus on if there were additional siblings. If there were, that means the padding needs to begin with a vertical line. So I'll take the pad builder and append to it the char v-line. Then with that, we also need to take into account spacing, because we've taken spacing away from here. So that means the spacing is still going to be handled by the padding. So after we add the one character, then we need to add some spaces to the end of it. So pad builder, append. Now what do we actually need to append in this case? Or how many spaces to append? Well, if we look back inside of the tree example, we can see, let's take this line that was higher up. In a case where we had all blank spaces, we know that there's 4 of them. In a case where there's a line, we have a line followed by 1, 2, 3 characters, or tree offset -1. So we'll append the space character for a number of times being tree draw offset -1. So that way we get our T-joint.
And 3 spaces.
Or excuse me, our vertical line and 3 spaces.
Right.
Exactly. So let me space that down a little bit. Now, if we did not have any further siblings, and at this level we're appending a angle, that means we simply need 4 spaces and no vertical line. So we can do pad builder, append. As a matter of fact, I feel lazy, so I'll just steal the current line that had 3 spaces, paste it, and now we're going to go for a full tree draw offset, or 4 spaces.
Right.
And that takes care of that. Now I believe all we need to take into account is all of the calls to show tree now are once again wrong because they're all passing an integer.
Including our call at the end of the method.
So first of which is the call at the end of the method. So we can feed it pad builder dot to string. So we get the newest result of our pad builder. And the other cases are going to be things outside of show tree, things like the instance show tree, which is now going to need to take in blank string instead of 0. We'll start off the padding as a blank string so we get no spacing off of the edge. And then we need to give the same treatment to the static show all. And now with that, we can build, and everything is building, so we should be able to run and see what our result is. Hey, very nice. So as far as tree drawing goes, we now have a properly drawn tree that mimics the tree utilities drawing version. So we can see that the A, B, and C represent this branch, or are similar to this branch, so we have a few indentions all immediately angled off. Or we can have cases where we have a few extra siblings, in which case we use T-joints.
Mm-hmm. Now, of course, it would be nice to go ahead and fix this up in such a way that we know we're rather looking at the scene root down, or we're looking at a specific node down.
And we could correct that easily by jumping over to the command that handles listing. So if I expand commands and then jump into the command ls, what we could do is, in the case of a show all, we could precede that by writing out the word scene so that it would show as the scene is everything.
Sure.
So we could do a console write line where we write out the word scene. which makes the entire tree look more complete. We see scene at the root, where we have our A and D nodes, and then subsequent subtrees off of those.
Of course, right now, if you type ls space D, now we have this. So we need to fix the portion that's handling just drawing from a particular node on.
And that's handled under this block, where we've determined the node to list from. So what we could do is, before we say tell that node to show tree, we could instead write out a line saying that node's name. So console.writeLine, and then we'll write out that actual node beforehand. Because if you remember a second ago, if I comment this out, you see an ls for D is actually omitting D. I mean, D is the root, it's just not shown, because we have nothing to show it. So writing out the name of the node before telling it to show tree will give the following result. ls for D shows D at the root with that entire branch. So we see this entire branch shown by itself.
Very nice.
Otherwise, we show the entire scene as the root.
Now if you were to take D and parent it to C, just to play around for a second.
So parent D to C.
And ls that, you can see that our engine is working fantastic. Very nice, very sharp. So that's really pretty much it. I mean, at this point, like I said, if you had any difficulty whatsoever coming up with the logic to pull this off, I highly recommend on a piece of paper drawing out a very, very simple hierarchy and then tracing through the method that Logan just put together and watching how this thing gets assembled. And I promise you that's going to have a lot of value if you take the time to do that. Now, let's take it a step further, Logan. In the next video, that's right, we're going to do one more video. Let's go ahead and create our very own tree command, or at least actually read a folder structure and show that folder structure out with the code that we've written here. So what I want to demonstrate, and this is just some bonus stuff that shouldn't take us but a few minutes to do. I just want to demonstrate how we can reuse a lot of the code that we just created to reproduce the tree command.
Right. Well, we've made this renderer based off of the tree utility, so that's going to be nice to see if we could recreate that actual tree utility.
Utilizing the method that we just put together. I think that'd be awesome. And if you guys would like to take that as a challenge before watching the next video, try to put it together yourself. Otherwise, watch the next video. Again, this is just some bonus material. We're going to throw it your way real quick, and then we'll move on into the XNA stuff. So with that, that is going to wrap up this advanced rendering challenge. Thanks a lot.